So Alex actually works on GCC and I kind of use the output. I do try to submit patches if I find something that doesn't look right. So for DWARF, I work on elf utils. And I added support for split-dwarf and DWARF5 this year, and from that I'm looking at GCC, how it generates DWARF5, split-dwarf, and I fixed a couple of things. DWARF is often described as translating your binaries, your addresses to source, but if that was all it was, then it's just a table of addresses to source files, and that's not it. You also want the types of things, the functions, what are the parameters, given variables, you want to know where in memory or in registers you can find the values, the location descriptors. You want to know the address ranges, what's covered by a lexical scope or by a function. If you're in a function, you might want to know where you came from, the call stack. And even if you just have the source, you might want to have all the macro definitions because you want to know what that piece of source code actually expands to. So DWARF is big. And there's lots of interconnected parts. At first I wanted to just go through all the lines and explain what it, how all the references work, but it's a bit too much. But what's interesting is that there are lots of sections with different pieces of the debug info, and they all reference each other. And this talk is a bit about how that can be made more efficient and how DWARF5 does that. Right, so if you really want to know more about DWARF5, go to the Dwarf Standard Store website. Look it up. It's this page actually has a nice summary of all the new stuff in it. So what I wanted to talk about mainly was the new and smaller data representation. One of the interesting things about the DWARF standard is that they have a lot of goals, design goals. I think a bit too many because they bite each other. But the interesting thing are the vendor extensibility. So we can often try out some ideas as GNU extensions, and then they get folded into the standards in a more generalized form. One thing that's really nice about DWARF and a bit of a problem, depending on how you look at it, is that it has a limited dependency on tools. So you kind of can see DWARF as just data that you copy around, or you really know what it is about. So That's really nice because the assembler, linker, other tools don't need much support to work with dwarf. To create dwarf and to combine it, you really only need 4 things. You have to be able to reference labels, especially labels between data sections, and that's what we going to talk about a bit, and be able to reference symbols. And then it would be nice if the assembler could produce LEB, L-E-B, how do you pronounce that? 128 format numbers, which are variable size, and always choose the smallest size to express a number in. And that's really nice because it means a linker just sees a blob of data like it sees code, has some relocations in it, resolves the relocations and concatenates the dwarf and doesn't need to know anything about it. And that's also kind of the problem. It's simple, but it has at least 3 issues in that since you don't know what's in the dwarf, you can't actually deduplicate stuff, and often in 2 source files you use the same types. The type description comes in both object files, and you just concatenate them together. The interesting thing is, at least I didn't immediately realize that relocations are actually huge and complex things. As you saw in the first diagram, there are a lot of intersection references, and for that, relocations are really far too complex. You don't need all the complexity. And a lot of data is just moved around, which is just wasteful. So for the first problem, what if we had a section group or link one section? And linkers actually have that. So let's do that. Then what you could do is calculate a hazard section over the bigger types and put those in special sections with the checksum as name, and then the linker could just deduplicate them away. So to do that, you need a different form of reference, which is basically the checksum. If you refer to a type, you refer to the checksum of the type. It does require, or did require in DWARF4, that there are new unit headers. You want to put the type ID in the header. And for DWARF4, that meant that you had different sections, the debug type section and the debug info section. Luckily in DWARF5, the header got expanded, maybe too bad because now the header is also big for non-type units. but at least you have them both in the same section again, which is so GC does this, but currently it doesn't do this by default, and one of the main reasons was fairly simple, that as soon as you break the die tree in different sections, a lot of programs just use offsets in a section, and even their interfaces, ABIs, have, a die is referenced by an offset, and now suddenly you had to add two. For DWARF5, it all became a bit simpler. Of course, in the object files you still have lots of concatenate sections, but maybe we could look at enabling this by default.
Well, it has major issues, I think, because when you're using debug types or debug info with the DWARF5 types stuff, you can always reference just a single die out of that unit, and that's a major problem, I think, because many times you have a structure and you want to refer to the fields of that or substructures and so on, and there's no way to express that, and then you have to duplicate it, and so sometimes it saves some amount of space, and other times it makes it larger and makes it harder for DWZ and
so that is actually the next thing. It's DWZ is indeed a problem. It doesn't know about debug types, and interestingly enough, it makes the next thing we're talking about, the split-dwarf, more complicated, because there you don't have a linker to combine the concatenate sections, so they just keep being in the split-dwarf. So, let's see. The other thing is that their relocations are really huge. They have the address, the offset they apply to, what kind of relocation they are, the symbol information, and then on various architectures there's also an addend, and a lot of that complexity is really not needed for intersection references in DWARF, because you already know or should know which other section you refer to, and GC actually generates a 32-bit dwarf, so your references could actually be smaller. So for DWARF5, a lot of thought was put into making the references not rely on relocations. So, for example, for the range list and the log lists, which are the ranges and logs from DWARF4, what you define is a base offset per CPU, so that's a real relocation, and then you have an index at the start of the table that you index into. Maybe I should have made a diagram, sorry. The nice thing about using the index table is that your references are now 1, 2, 3, or 4 bytes big, and with just one relocation per. What did happen? Could you type your password?
Oh man.
So, yeah, sorry about that. Oh, that was quick. Okay. So replacing the relocations is really nice. It is a bit more work for the producer because it has to keep track of all the indexes and offsets. But it does really save a lot of space, and there's a lot less work to do for the linker. Interestingly enough, since this work was originally done for split-dwarf, GC currently only does it when it generates split-dwarf. Yeah, what does it depend on?
Like the debug lock list section and stuff like that is enabled by DWARF5, and that's beneficial unconditionally. And there are then stuff that's only useful for the relocation size, but some of those changes made for split-dwarf are that they reduce the amount of relocations a lot. So if you ship many static libraries with debug info, then it's a win, clear. But if you link that stuff into a shared library or a binary, so something what Linux distributions typically do with their packages, and that's what those distributions care about most, then you actually get bigger debug info because of that, because there is an indirection and extra references. So while the relocations are put into an array or something like that, but you need to index that array, so there's indirection and it grows the size. And if the tools like DWZ is taught to undo this, if it's size optimization, then we can of course turn it on by default. Until then, it maybe should be another GDWARF option so that users can select, do I care about relocatable objects most? And for stuff like the Linux kernel, yes, I do, because that's how I ship the stuff. Then yes, turn it on. If I do care most about the sizes of shared libraries and binaries, don't turn it on, because and then of course there is the Google usage module where you have huge binaries linked by massive parallel environment, and then of course you want to do the split-dwarf, which is another thing.
So maybe that gets us to the next part, the split-dwarf. It does look no, let's just first go to the split-dwarf. How much? 5 minutes? Okay, quickly, Mark. So indeed, so we got rid of most of the intersection references. Now, what if we could put everything that doesn't need relocations in a separate file, a DWO file? So we still have some relocations, obviously for the addresses and for attributes referencing strings. But what we could do is create a skeleton die tree that has all the stuff that needs relocation, and then add a new debug address section that just contains the addresses that need to be relocated, and then anything that refers to an address, like in the previous case, can just index into the table. And for the string references, because indirection is always a solution for everything, you introduce a string offsets section. in the DWO file. That's not directly needed, but it is needed when you combine them again. The obvious problem with this is that it gets pretty complicated. So on the left you have all the stuff that still has relocations in it that will be put in the object files. The linker can combine the left side, and everything that doesn't need relocations you put in a separate file that you don't touch anymore. It's pretty awesome for your normal edit compile debug cycle. It does again require the producer to keep more information. And funnily enough, the duplications come back because the linker isn't there to deduplicate them, and the dwarf consumers do need to be a bit smarter. For example, when I was working on the Alvutal support, I happily opened all the DWO files before reading them, and of course you run out of file descriptors as soon as you do that. You can package them together. Let's just skip through this. Or you could actually, if we are working on recognizing the dwarf, have a tool that really does duplication. But the problem at the moment is consumer support is pretty good for DWARF5 or split-dwarf. GDB supports both, but not together. That just needs updating for the DWARF5 split-dwarf variants. Alvutal does both and both together, but not together with debug types. Yeah, that's the real problem is kind of in the that was the wrong button in the where, and I pushed the wrong button. Oh, well. I should have.
I should be able to go back.
Oh, right, yeah. The problem is in the distribution tools. So DWP only does DWARF4, split-dwarf, not DWARF5. DWZ only does DWARF4, no debug types, no split-dwarf, RPM debug edit only does DWARF4. So these are kind of in the middle of GCC and the actual producers.
One for DWZ was, I think that DWP was able to undo the split-dwarf, convert the split-dwarf back to the normal dwarf, and then DWZ can compress it, but probably DWP didn't gain that support, and of course DWZ doesn't support the DWARF5, which has the support for DWZ standardized, but yeah, nobody implemented it.
Okay, these are my wishes and recommendations. I wanted to say part of it is the DWARF5 split dwarf wasn't completely correct, so GDB is excused to not completely support it. It's fixed in trunk, but probably should be backported to 8.x. Well, I'll give it over to Alex, who actually explains how the debug. Oh, this one. Do you want this? Or that?
No, I prefer this one. I guess. Can you hear me? Can the recording hear me? Thank you. So let's switch to a different layer. So can you hear me now? Good. Okay, is this loud enough? Good. So I'm going to talk about this project that I've been working on for a few months now, that I named Geology, because it's the study of optimization and debugging, right? O and G. So I'll talk about a bit about the project per se, some of the assumptions that guided the conclusions in a way, and the main highlights, because it's such a huge output that I'll mention that I can't possibly just cover everything. So the idea was to figure out what kind of impact optimizations had on the ability to debug programs or to monitor programs with tools such as SystemTap. And optimize programs, obviously. That's what I've been working on for a very long time. So for this project, I went through all of the optimization passes in GCC that are enabled by -O anything you can imagine. And that adds up to 140 different flags and an infinite number of passes. So it was a lot of work. So every pass that is enabled by one of these O flags and that is not enabled at O0, or that even if it is enabled by O0 but it is somehow modified by these flags, then I looked at that and I tried to figure out how good the debug info that we generate how well it is preserved, so that we can in the end find the information that we need. So I worked on GCC 8, the first release out of the GCC 8 branch. That was when I started. I mentioned GNU/Linux, though I'm not sure that's important. The important bit is the assembler and maybe a bit of linker support for location numbers. But aside from that, yeah, different. DWARF2 and that's
exactly.
There. Thank you. That's exactly what I was thinking when I wrote that. So yeah, basically ELF and DWARF. The debug info formats and choices and defaults. Those have to do with the defaults for GNU/Linux. So GCC has for a very long time had file number, line number, column number. That's more recent to some extent, but it was already there for a long time in ranges and lexical blocks. This is all encoded in tree expressions, in Gimple statements, in RTL instance and stuff like that. So it's been there forever. It is one of the things that I looked at about being preserved. Variable tracking is also very solid, robust, and old, in a way, technology. In which GCC uses annotations in registers and memory references to figure out what variable that reference has to do with. And I looked at how well that is preserved. VTA is getting old. It's some 10 years old now. And with this, we add annotations to the internal representation that bind source variables to something that holds the value of the variable. Ideally, it's a register or a memory location, but it might be optimized into an arbitrary expression that will then be able to represent in debug information. But it only covers scalars, never addressable memory. That's for VT alone. Statement frontiers are a way to mark in the internal representation a point in the program. And when you reach that point, the idea is that all of the previous side effects have taken effect, and none of the future side effects have taken effect yet. So that's sort of the magic that I try to abstract into a statement for 2 years. And location views are a way to represent that in line number encoding and debug information. So it's there. Although it's not yet supported in debuggers and monitors, I have worked under the assumption that someday they will be. So in cases in which you currently may seem to lose information, but the information is there, I concluded that it's not our problem. It'll take a few seconds, but it will be back. I took the assumption that we do have the information, and well, the debugging tool or the monitoring tool will eventually be able to use that. So there's nothing in GCC that needs improvement. So when trying to figure out what optimizations break, I made some decisions on what kinds of breakage are important and what kinds are not. For instance, sharing may cause early death. That's very antithetical to the free software movement. But the idea the idea is that if you assign a variable to a certain register and then the variable dies, and then you reuse that same register for something else, well, this will never happen in a non-optimized program. So we will never realize the variable died. So if you were in a debugger and looked for the variable at a point in which it is dead, you would still be able to get its value in the non-optimized case. But in the optimized program, it might no longer be there. And that's not a problem. I decided, because the variable is actually dead. So we're not losing anything, we're just, well, that's truth. The variable is dead. We're actually getting a better representation in a way.
There are two cases. One is if it goes out of scope, then of course there is no need to track anything. If it's still in scope but dead, then some people might want to check that.
No, see, if it is dead, then it's dead, Jim. So, I mean, I took my conclusions based on these premises. Of course, they're all open to dispute it for anyone who wants to redo the work. I mean, anyone is welcome to redo it under different assumptions. But I documented these so that if you don't agree with them, you can go and recheck stuff. But I mean, I think it's important to set the ground like that. When you tell a debugger to stop at to set a breakpoint at a certain address as opposed to, say, a label or a function or a line number, if you use the actual address, then, well, sometimes the compiler will duplicate basic blocks, and then you set the breakpoint at this one address. You won't catch the same point in the program in a different address. This is not a problem. I mean, use the logical reference to the location that you're interested in, and then the debugger will set 2 or 3 or however many breakpoints you need to stop at that point in the program. Setting variables in the debugger is tricky. Sometimes a variable is located in several places at the same time. We don't keep track of that. We know, when we're lucky, one location for the variable. I decided that I wouldn't be concerned about cases in which a variable is in multiple locations and you want to modify it, and you modify one of the locations, but then the compiler goes and reads the variable from the other. But I wasn't sure about that. I wasn't sure this was a good decision, so I actually made it a point to note every time that this was a potential risk that, or try to anyway, that this could happen. But there are a lot of places like that, so I probably missed some. There's also the case in which the compiler makes an optimization decision based on what's in the program. The variable can hold this or that value. So I know that this branch will never be taken, and then the code is removed. Now, if you go in the debugger and modify the variable so that the test would pass and you would enter that block, well, so sorry, you won't get the code back from the data. So I do not regard that as a problem. But again, I mentioned issues in which you have a question.
I just want to make sure here in the optimized out case that you make the distinction of telling the user that the variable is dead as opposed to showing the wrong value.
I see what you mean. So back to the first point, right? When a variable is dead, the idea is that you get optimized out, not that you get the wrong value. Okay. I mean that is a serious mistake that deserves a note saying this is wrong. We have to fix that.
Okay, good, fine, thanks.
So in the end, there were 140, if I remember correctly, different compiler flags. Let's start with the first one. No, I'm kidding. There are just too many of them to go through now, so I won't do that. If you want all the details, there is a report. It's so far a draft, work in progress. There's a link at the end of the presentation. It'll be better formatted eventually and published in a proper way, but so far you can already look at it and see what sort of stuff I found out. But I have some highlights that I wanted to bring to you. First thing I was very happy to realize was that the introduction of VTA and debug bind annotations and then the debug markers was quite seamless. I mean, it did not cause a lot of trouble to most of the optimizers. It just fit in, especially when it comes to SSA. It's sort of, things are better connected and organized in SSA for the particular representation of debug binds. So that helped a lot. And for RTL, that's not so easy, but it still mostly worked. I mean, passes had to be adjusted in a number of cases, not just to ignore debug binds and markers, but in some cases actually adjust them properly, and sometimes that took some effort. But in most cases, it was not a lot of effort, which was good to verify. For me personally, because I was involved in the entire project. Part of that is because we have some logic to preserve binds even when they go, even when the variables are dead, in a way. So there is logic to preserve stuff when you say remove a statement. We will try to retain the binding if it's referenced elsewhere, so we don't lose the debug information. That's all very much automatic. You don't have to work harder in the optimization passes to get this side effect. Now, we could do better. Some API choices led to somewhat unfortunate situations in which, depending on the order in which you move, or remove or insert other statement, or move the same statement, the result is different. So I'm trying to find out some ways to improve that, and get not the same results, but get a better API for this sort of modification in the internal representation that several optimizers need to do to preserve more debug information. I also found out bugs in various passes, and they're documented for fixing in the future in the report so far. I found out another problem that I hadn't realized was so deep, that has to do with a variable becoming a scalar late in the compilation. If it was addressable, but you could remove all of the address taking and referencing, then it becomes scalar much later, and then you can't go back to the beginning and mark and output all of the binds that should have been there, so they could end up in the wrong places or not be there at all. So I'm trying to figure out some way to improve that. Another surprise was that there is one warning flag that actually modifies code generation. Well, I noticed this one because it actually enables a pass by itself. And it wasn't, this pass, most of the code gen changes in it are guarded by other optimization flags, but there was one that isn't. So this should be pretty easy to fix. Now, there are a number of passes that lose track of variable information. Locations and values specifically. So, there are passes that just disregard variable locations altogether. The delay slot optimizations, they're enabled even at OG. They actually mess things up pretty badly. They run after variable tracking, and they just don't pay attention at all to the bindings. So
what it actually means in the debug info, where we stick the information because of the delay slot.
yes, there is that too. But I mean, we move instructions from one place to a different place, sometimes modifying a register, and there are places in between that refer to the register as if it hadn't been modified. So that's bad. I mean, that's wrong. I have no clue how to fix that. It should be really hard. Same thing for peepholes. They can even drop bindings from between different instructions that are combined in a single peephole. So, I mean, that's a problem. It's documented. Now we should go out and fix it somehow. Auto increment also messes things up. It can, the same thing, you can modify a register and not adjust binds between the point in which it was modified and the point in which it would have been modified originally. So we end up with incorrect stuff. We have a number of passes that remove memory stores, or that move memory stores around, like data store elimination, or syncing in trees. Those can actually create problems now because we don't have annotations like those in VTA for addressable variables, which would be affected by these optimizations. And these run even at OG. So there is an opportunity to improve here. Now, when it comes to vectorization, that actually reorders a lot of operations. That I consider, yeah, that's so for now. I mean, with the current infrastructure, we cannot represent that reordering at all. So I decided it's hopeless for now. But Yes, with some extensions.
Basically, in the dwarf consumer, in the debugger, you would choose, I want to see what the third lane does, and then just look at that part of registers or something.
Ah, interesting. I'll think about that. Thank you, Jakob. Then there's the issue of dismembering types. Like there are several passes that break up like complex numbers or structs into scalars. And they don't do a very good job of reconstructing the original objects in debug information. So there's an opportunity to improve stuff here. Particularly IPA, SRA, it just drops on the floor the very existence of a parameter that is split into its components.
That should be covered by the parameter ref opcode, which...
you mean there is a dwarf extension for that, but there isn't. GCC does not take advantage of that, as far as I know. Since when?
4 or 5 years.
Really?
Yes.
Oh, well, then maybe I missed. But I'm pretty sure I saw a problem there in GCC 8. So, oh man. Anyway, there's this other crazy idea that I had the other day, several years ago actually, that there are a number of passes that reorganize the counterflow graph, and some optimizations that do that too, in a way, and they actually drop markers and binds if they're in otherwise empty blocks, because the blocks seem to be empty, and so it could, in theory, be just removed. And in several cases, we actually just remove that, and then we discard a lot of information. Turns out that we could preserve that in some cases already. In other cases, we need to be able to tell, okay, you want to stop. You want to stop at this point in the program now, and you want to take this bind for this variable only if the guarding condition that I managed to optimize away applies, or if it doesn't apply. So you mark the several markers or binds with conditionals, so, and then somehow represent that in dwarf so that the debugger can step into a block that was optimized away. Your face is very interesting, Jason.
Setting variables being complicated in optimized code is that there are various optimizations based on what we know the variable can be, and trying to recover the optimized state only in the debug information seems more difficult.
It's a hard problem.
Than
Absolutely.
it's worth.
So I'm thinking of, for instance, a switch statement that is turned into a sequence of conditional statements. And then, well, we can still note that when you execute this conditional statement, its effect is also conditional, for instance. And you only get there if that other condition was met. So this might take a lot of effort, but it might be worth it, because there are a number of passes that currently drop useful information.
So on the topic of setting variables in optimized code, I understand that this is difficult in the general case, but on the other hand, I think most users would probably understand why that doesn't work. The bigger problem is that it appears to be working, because you can set it in GDB and it will do something, but then weird stuff will happen. So instead of trying to make it work, can we try to make it fail
it not work.
reliably, so that if you do the set in the debugger will tell you, sorry, you can't do that right now because it was optimized.
Yeah, there are two situations that I think are important to cover. One is when a variable is in several locations at the same time. That is easier to cover. The other, in the GCC, I mean. The other is when the same location is shared by multiple variables. That is something that the debugger could somehow tell and maybe warn the user. So yes, there are concerns about that. But
I mean, you could express this in DWARF even today, I think, by using something like a DWARF location if it's modifiable, but a DWARF expression if its value can be read, but it cannot be modified. So
ideally, in DWARF, we could actually represent the multiple locations. We don't do that.
Well, yeah,
but maybe we should. That would be a lot more expensive than what we do now. But yeah. Almost wrapping up. So loop optimizations very quickly. I'm breaking something here. I'm sorry. So I was surprised to find out that a number of loop optimizations are actually okay when it comes to debug information. Because I thought, well, there's no way. I mean, they're not all. They don't all mess up the code in unrecoverable ways. So, but there are some that actually do. Whenever you change the iteration space, the order in which you visit each iteration, then you're sort of in no man's land when it comes to debug information. There are also cases that we could do better when we optimize induction variables. We currently may substitute one or several induction variables by one, and we don't map back. Or we may just remove stuff, the original variable and the induction variable that replaces it is not a good representation for the original variable. We just lose that. So we could improve that. And finally, two particularly tricky cases that can use crazy ideas that I mentioned. Well, one is partial inlining. We currently don't deal with that very well at all. But we need some extension to be able to link one part of the function that was kept out of line back to the other part that was inlined. And if we get that, I guess a lot of the issues just go away. Yes, Jason?
Like that extension to also say the reason for outlining, so that because next to partial inlining we have OpenMP parallel regions, OpenMP tasks, and OpenMP target regions, OpenACC target regions, and all those should be expressed in the debug information so that the debugger knows, okay, this is this kind of region, I can expect something, I can call this plugin to do something for me, or I can just do it directly, and so on.
Yep.
Is there a reason we can't use the normal tag inline subroutine for partial inlining?
We can use that for the fragment that was inlined. But what I'm getting at is that there is a fragment that was inlined and another fragment that wasn't. And we don't have a way to express that this fragment is inside or is the other part of one abstract function. So you have some variables declared here and also here, but they are actually the same variable. Stuff like that. I mean,
probably should use stuff like the abstract origins of the lexical blocks, which are fully inside of the moved region, and point that back to the origin. But then there are the boundary lexical scopes, which are duplicated partially. And
so let me just cover the last point, then we go wild. Identical code folding is terrible for debug information right now. Like we get one function with its debug information standing for a completely unrelated function with different variables, different stuff. So
It's the jump story.
yeah. So I thought, hey, maybe those conditional binds and markers that I mentioned could be used to fix that. Like when we merge a set of functions into a single internal representation, we could retain all of the annotations that they had with conditional, saying, if I'm running this one function, then this is the effect on debugging. If I'm running this other function, then there is this effect, and so on and so forth. And then we somehow, wave hands, encode that in dwarf, and things magically work. So that's what we can probably identify at runtime which of the variants we're running based on the callers. And in several cases. I mean, even getting that for several cases as opposed to all is better than what we have now, which is very, very confusing.
But you probably need separate set of line tables for each of them.
That's one possibility. Yeah, this is sort of implied here. You might need different line number tables. You probably want different dies for the functions and location lists and stuff. So yeah, it's not easy, but it is something that is in my radar. That's all I had, so thank you so much. This link here will point to my webpage, so you can see it now. The report is available there in a draft form. Wrong password. And we are now open for discussions, questions. Thank you.